Hi guys, I got another arcade PCB for repair. This is a non-working Double Dragon board, which I got off of eBay pretty cheap. It was sold as is, non-working for parts, no actual precise description of what the problem with the board might be. But as always, we're going to go through the repair step by step together and try to get the board back to life, whatever the problems with the board might be this time. So as always, the first part is of a board repair is always the inspection of the board, and I just took it out of the box, but I already took a look at it, and this is the top board, which is the CPU board. And aside from looking pretty dirty and dusty, I don't have any major concerns with it. There seem to be no missing parts, no problems visible with the trace. There's no corrosion or anything. It looks pretty good, actually. It surely needs a clean, but that should be all, really. And this is the bottom board, which looks actually pretty clean from the start, and also here I don't see any issues with missing parts, corrosion, or anything like that. So it's looking pretty good so far. I'd say we hook up the board to our test station and see what it does. Okay, I hooked the board up to my test setup over here. So let's take a look what it does. Okay, looks good. Well, it's starting up, but there's some graphical glitches going on. The dragon is somewhat okay. Okay, the background seems to be okay. Also the text on the screen, like time, credits, but the sprites, well, actually it looks like every second vertical line is missing, or maybe well, yeah, not even missing, but like some stuff is going on this side here. And also you could see some random glitching going on in the middle of the screen, or over here, and sometimes there's some lines there. Okay, but I think overall that's quite good. The game's actually running. This issue should be caused by a problem on the graphics PCB, and I think we should be able to find the fault and fix the board. We could actually see if there's okay. So sound is working. So overall, not too bad. Okay, so now where do we go from here? Where do we start our repair? I was just looking at the Double Dragon schematics, and it hit me that the situation is actually quite different to the situation we had with the last boards that I did repair videos about, because those boards at the beginning had both had some major faults which let them not start up at all, but as we did already see, the game is actually running, and we have a very a very specific problem actually with the sprites, which we can define quite pretty clearly. So we can say the background graphics are okay, the text is okay, the sprites have missing lines, and somehow every second line is missing, and the contents of those lines appears to be spread randomly on this particular line. So knowing that, it would actually be a good idea, maybe not as with the other repairs, start poking around with the Logic Pro, but actually looking at the schematics and see and take a look, try to understand how the PCB actually works, at least to some extent, and then think about what possible reasons could there be on the PCB to cause this issue. And I think we will actually be probably able to narrow the problem down to a few chips by actually just looking at the schematics and keeping in mind what problem we're actually seeing on the screen. Okay, before we actually look at the schematics, I wanted to show you this photo I've taken of a Double Dragon PCB. This is actually the board from my last repair, which you can see because I put some stickers on those chips here. But what I did here is actually create a color overlay, which I can show you here, which gives me an orientation of what parts of the board are connected to what parts of the schematics. And over here you can see the color code. So the objects, as they are called in schematics, are it's 5 pages of schematics, 3 to 7, and the chips that are on those schematic pages are the blue ones over here, the yellow ones, and those EEPROMs over here, and the chips down here. So quite a few chips are actually used for generating the sprites. The red and green chips down here, together with the quartz crystal, generate clocks and counters, and the violet EEPROMs up here, and those brown chips up here, those are for the backgrounds. That's actually a smaller part. So our issue has to be probably somewhere in this this area here. Okay, also before we start looking into the schematics, we might want to recapitulate how the sprites are actually generated on the screen on the level of the PCB. And to show this, I just wrote up this little scheme here, which might be a bit trivial in the end, but just to recapitulate, at the base, so to say, of the sprite circuitry always has to be a counter which actually holds the current horizontal and vertical position of the place where the screen is actually being refreshed or drawn. So the sprite circuitry actually knows which part of the screen or which place on the which spot on the screen is actually relevant at the moment, and can determine for this spot if actually it needs to display some sprite graphics or not. So there always, as an input to the circuitry, there's always a horizontal and a vertical screen position, which is also the case for this PCB. You can see here on the schematics, and this is also part of the bottom PCB of the graphics PCB. It all starts with a quartz crystal down here, which is sent through a series of counters, and what we get as an output is this 8-bit horizontal position address, which is called HN over here, and we also get on this part of the schematics an 8-bit vertical address, which is called VPOS. So that is the basic input for the sprite circuitry. Also worth mentioning in this case is another single line, which is called V1, which is actually a copy of the least significant bit of the vertical position. It's a separate signal that's coming out of the vertical position bus. The least significant bit is also called V1. Okay, getting back to my little scheme here. So the horizontal and vertical position are normally, as a next step, connected to some sort of video RAM. So the horizontal and vertical position are used as an address in the video RAM, and the data at this address in the video RAM is usually the information about the sprite that needs to be displayed at that location. Pretty simple actually. And of course, what I mean by this, the CPU must be able to access the video RAM and change its contents, so it will be able to move the sprites around or generate new sprites or remove sprites from the screen or whatever it wants to do. This can be found in the schematics actually here. This is a RAM chip, which is addressed through these 8 lines. These 8 lines are actually either the horizontal counter, or they are some sort of CPU address bus, which can be switched over through these multiplexers, which are put here in the schematic, so that you can also see it here with the you also have a data bus connection here, so the CPU can write some data into the RAMs, and also the RAMs can output their data further up here into the rest of the sprite generation circuitry. Okay, and what then happens is that the data usually sooner or later is fed into some EPROMs, which contain the actual graphical data and the colors that need to be output on the screen. And this is when this very, very basic schematic sprite circuitry is finished and the sprite is appearing on the screen. Okay, so getting back to our problem at hand, regarding the missing lines in the sprites, I actually found something very interesting here in the schematics. This is the part that I actually just showed you with the video RAM, and what I noticed is that there's actually some sort of a dual architecture going on here, because this part here is actually identical to this part over here. And as it turns out, there's 2 RAM chips, and they are both connected to the horizontal counters and to some data buses, and in the end they are both their outputs are both connected to the same bus up here behind those registers. And what you can actually see is that the circuitry is actually created in a way that from one line to the next, the RAMs are actually switched, which are being used to generate the graphics in this particular vertical line. So you can see the signal line V1, which I mentioned earlier, which is which was the least significant bit of the vertical position. It is feeding into the registers, and also it is also feeding in here into this multiplexer, and what this causes is that, for instance, if the screen is starting to be generated and we're at the top line, line 0, the graphical data for this line is taken from this RAM chip and output through this register up here into the later parts of the sprite circuitry, and for the next line, which is line number 1, which is an odd number, the circuitry is switched over to here, and the graphical data for this line is taken from this RAM chip, and then again, getting to line number 2, which is an even number, it switches over to this chip again. So it's always switching back and forth per line based on this V1 signal between the RAM chips. And what you might ask yourself is what could be the purpose of this. And actually I think it's pretty simple, because I think what is happening here is that, for instance, the first line on the screen is drawn using this RAM, and while this line is actually drawn on the screen, the CPU has time to prepare the next line, or the sprite contents of the next line, in the other RAM. So while this line is being drawn, the next one is being prepared over at this RAM, because the outputs are shut down and it's connected to the CPU. When the first line is finished, this RAM takes over, displays its content, and while it is doing that, the first RAM can be accessed through the CPU and can be prepared with the contents for the next line. That is probably the reason why there is this dual architecture. Okay, and if you're asking yourself, why am I telling you all of this? Well, that's because I think with this board there's actually a problem with this dual architecture, because what I think is that one of the circuits, it's working right and it's displaying the correct stuff on the screen, but the other circuit to which it switches every second line actually messes up the graphical data and bounces it all over the place. So actually what I think is that either this part over here is not working right, or this part over here, which is only 4 chips. And again, looking at the screen and looking at the last lines down here, you can actually see that the problem, because you can see the problem in the lower lines, you can actually see that the problem appears to be with the lines that have even numbers, because the last line down here seems to be okay, but the line on top of that has scrambled data. So probably the even lines have are affected by the issue, and in the schematics that would be this part over here. So the problem should be in one of those 4 chips down here. So let's look at them on the board. Okay, and on the board the suspects, our top suspects are those 4 chips, 81, 82, 63 and 64. it is very, very, very likely that a failure of one of those 4 chips might actually will actually cause the problem that we're seeing. And the interesting thing, or the funny thing, is that we were actually able to determine that without even fiddling around with any logic probe or any other instruments. And also I have to say that probably with the logic probe you wouldn't even get to the bottom of this problem in this case, because it's very likely that all of the lines around here are wiggling anyway, because they are connected to several buses. Yeah, so I think this was a very nice way to determine the problem. I hope that I'm right, at least. So what you could do now is actually just replace those 4 chips, because those TTL chips will actually cost you a few cents. This may be $1, $2, $3 for the RAM chip. The most likely suspect of those 4 is probably the RAM chip, I'd say, because I've seen there are several RAM chips on the Double Dragon board, and I've seen some of them fail in earlier repairs. So I think this is the top suspect over here, but you could change those 4 chips and would be very likely that the board would be up and running again. But in this case we're actually gonna go a bit further and look at this RAM chip, the inputs, the address lines, the data lines, on the logic analyzer to actually see if the chip is working right or not. Okay, so I hooked up the logic analyzer to the Double Dragon board, to the IC81, which is the RAM chip, and the game is running. You can still see the problem here, and I already took some samples from the lines that I hooked up. I did connect the address lines, the data lines, of course, also the write enable signal of the RAM, and for reference I also put one of the probes on the well, I think you can see it's down up here from the chip next to the V1 signal. Okay, so and here's how it looks on the logic analyzer. You can see the write enabled signal up here. The address values are displayed over here. The data is this line here, and this down here is the V1 signal. And what you can see here is that the V1 signal is toggling from high to low, as expected, with the vertical line frequency. So, and if we zoom in on this, maybe like this, we can see that we're now at a point where the V1 signal is going from low to high, and that means that the outputs of the RAM aren't really connected to the video circuitry behind it. If the V1 signal is high, that's the time when the CPU has the possibility to access the RAM and put some information into it, and after it's finished, the V1 signal will go to a low state again, and when V1 is low, the video RAM's content is actually output to the display. So at this point the CPU should be writing to the RAM, and that's actually what we can see here. The signal is going high, the address bus is set to 0, and then the CPU is actually putting a value of F0 to the data lines, and then it's pulling the write enabled signal low, which means that it wants to write this value to the RAM. After that, it switches over the address to 1. At this spot, the RAM obviously has a value of 0, which you can see here, but then the write enabled signal is pulled down and the CPU writes a value of 80 at this position 1. And then it goes on like this. At position 2 the CPU is writing a 3, at position 3 the CPU is writing CA, at 4 it is writing C0. Then the CPU actually skips some positions, so it doesn't write anything to 5, 6 and 7, but at 8 it wants to write an F0, at 9 it wants to write an 80, at 0A it wants to write a 3, and so on and so on. And what we're going to do now is we're going to scroll forward in time and to this spot over here where the V1 signal actually is going low, because that's the time when the signals are going to be output into the graphics circuitry. Okay, so we see here that the V1 is going low and the address bus starts at 0 again, and this time, as it's connected to a counter, a horizontal counter, it won't skip any values like we saw just when the CPU was writing the data, but it will go like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, and so on, not skipping any values. And now we're going to check the data lines, what the CPU actually, what the RAM actually does. So, okay, so the address is set to 0. Right here, the data bus is a 0. So that's not correct, because, as we remember, I wrote it down actually for reference. At the address of 0, there should be an F0. So that's not correct. At 1, address 1, there's also a 0. Not correct. There should be an 80. Then we move ahead to this spot. Address 2 is an 03. So that is actually correct. Address 3 is an 98. Excuse me, yes, address 3 is 98. No, it should be CA. That's wrong also. So what do we have? Address 4 is A0. It should be C0. Address 5 is A0. Address 6 is A0. Address 7 is A0. That is correct. The CPU didn't write anything to those locations. Address 8 is A90. That is wrong. So all the data that's coming from the RAM is actually, not all the data, but most of it appears to be incorrect. So that is actually the proof that this RAM chip isn't working correctly, because here on the logic analyzer we can see that certain values are written to certain locations, and just a split second afterwards they are read from the same locations, and the outputs are different. So you can't prove it any better than that. I think that this RAM chip has to be non-working. Okay, I actually removed the RAM chip, the faulty RAM chip, and I'll actually have to get another one on the web. I don't have a spare chip ready right now, but I just thought we could fire the game up again and take a look how it looks. Yes, okay, the problem is still there, of course, but what is very nice is that the flickering stuff and all the garbage on the side of the screen are also gone, so which were caused by the corrupted data that the RAM chip did output. So I think this proves that we're on the right track, and that a new chip in this socket should actually fix the problem. I got lucky and I found actually on an old PCB a RAM chip I could use for this purpose. I desoldered it and already put it in the socket, so let's see what we get. And ta-da! Okay, the title screen looks good. So let's check the sprites. Okay, and here are the sprites. Working fine again. Okay, so thank you very much for watching the video. I hope that my videos might help you with your own arcade repairs. If you have any questions or comments, please post them at the bottom of this video. And of course, if you liked my video, please take a look at my other arcade repairs and think about joining my channel. So again, thank you very much.